This is 6.3. Today we're going to be discussing electrical power. Basically, for every electrical device that we want to run, we have two options. We can either plug it into a wall outlet, or we can put in enough batteries that it can go by itself. So those are our electrical sources. Batteries work by converting chemical energy into electrical energy. Sometimes they're rechargeable batteries, like in our cell phones, but eventually all batteries wear out. There's been great advances in our battery technology over the last 15-20 years, which makes small pocket devices that are energy hungry like cell phones possible, but there's still a very real limiting factor in terms of things like electrical cars. How do we make batteries that are safe enough, that can hold enough energy, that are also rechargeable, is a real issue that's hindering some aspects of our technology, and hopefully we'll have some large breakthroughs over the next decade that will really change up how we can drive around, things like drones, or all sorts of independent, not plugged-in things. Anyway, and then the wall outlets use energy from generators. Generators convert mechanical energy into electrical energy. There's lots of different types of these. Coal-burning power plants, nuclear power plants, hydroelectric dams, geothermal power plants. But they all come down to more or less the same thing. We need to create spin. And the usual way to do this is by heating up water. The water converts into steam. The steam turns a turbine. There's magnets on the edges of the blades that create a rotating magnetic field which generates electricity. Okay. These also represent two different types of electrical currents. Direct versus alternating. This was actually a really controversial field of research with Edison and Tesla a long time ago now. Basically, Edison was pushing direct current and Tesla was pushing alternating current, and there was a huge amount of public debate because when we were wiring up our electrical grids, we had to pick just one. With direct current, the charge moves in just one direction. We're pushing it from a positive pole to the negative pole. Or other way around, sorry, from the negative pole to the positive pole. What did you say right the first time? I don't even know. Not that it matters very much. Anyway, this is how batteries work. This is why, for example, if you have your batteries in backwards, the circuit won't work. With alternating current, instead, the charge moves back and forth and creates sort of a vibration. Here in the United States, we use a 60 hertz vibration. In Europe and other places, they use slightly different vibrations, and so it's not standardized worldwide. Our European friends have to buy adapters and stuff like that if they want to plug in their European electronics into American outlets. But the idea here is the same everywhere. This is what we use in our electrical and our wall outlets, in our household electrical circuits. The circuit ends have to switch poles rapidly, positive to negative, positive to negative. But that allows for this back and forth vibration, and we sort of harvest the energy out of it. And it turns out that alternating current works a lot better for pushing the current long distances. Because each electron is just vibrating in place, we're not trying to push electrons through an entire wire. It's just a lot easier to do. But there was like huge amounts of fuss about which one was going to end up being the dominant version, direct versus alternating. And in fact, there was even, this was a particularly horrible story, Edison even arranged to have an elephant electrocuted as a demonstration for how dangerous alternating current could be, which is slightly ridiculous because direct current is just as much. It's not which type of current you're using, it's the amount of amplitude and voltage that's running through it. The elephant had been condemned as a danger because it had crushed its handler at the zoo, and they turned it into this big public affair where people came out and watched the elephant be electrocuted, which is just horrifying. But times have changed. Okay, so how do we measure how much electricity we're getting? This is called electrical power, measured in watts. You've probably heard of this. If you haven't, ask your parents about your electrical bill. This is what it's measured in. It's the rate at which the voltage is being transferred to non-electrical energy. Measured in watts, where 1 watt is 1 joule of energy per second. And we actually more familiarly see kilowatts, kW, on like our bills and stuff like that, because 1 watt, 1 joule per second is not a whole lot of power. We have a couple different equations here. Power equals I, current, times the voltage, or power equals the current squared times the resistance, or power equals the voltage squared divided by the resistance. Where our P is power in watts, I here is current measured in amperes, delta V is voltage measured in volts, and R is resistance measured in ohms. So you're going to be applying these different equations based on what type of information you get. Did I give you a current and a resistance, or a voltage and a power, or what am I asking you to find? So you have to pick which of the three equations applies, and then solve for the missing variable. But other than that, it's pretty simple. Anyway, that's it for the video for today. I hope everybody's doing well, had a good weekend. Keep in mind this week's only got 4 days, so we're going to have a nice short week and a long weekend, and then we'll pick it up again next week, is the plan. Have a great day. Bye.